everybody. Thank you for the nice welcome. It's great to be here in Moscow, my first time in Moscow and first time in Russia. So hopefully, I like it so far. Hopefully you will like as well the talk I'm talking today about. So let's get started. First, I would like to tell you what I'm going to talk about. So if you find out, that's not what I expected, feel free to leave. Don't worry, I'm not going to be offended or anything. And we're going to cover, or I'm going to try cover, first the networking stack architecture and evolution, actually, of the architecture we have across the .NET Framework, UWP, and .NET Core. Next, I will actually talk about networking stack in .NET Core, more about direction and our plans, and then even status and some perf results that we are hitting. And hopefully, I will get as well time to cover the general BCL performance thoughts and observations. So hopefully, I'm going to get there. So let's get started. What I wanted to tell you as well, if you wonder why I'm talking about networking stack, the key reason for me is that, first of all, I'm on the team that deals with basically owns the networking stack across .NET Core and all other platforms. And the fact that I'm talking about and that networking stack is right now kind of very cool, very more needed because all the cloud stuff and microservices. I'm going to talk mainly about the client stack, not that much about the server stack. And if you wonder why, again, BCL and networking, and why I don't cover, for example, GC and other things, all those other things didn't fit into the talk. So I chose basically what I'm kind of most passionate about right now. There are also investments into other places of the runtime, .NET Core, and everywhere. The fact that I'm talking about these things doesn't mean that this is the only thing that we're investing into. All right, so let's get started for real. I'm going to cover the three main stacks that we have. That's the .NET Framework, which is the thing that kind of you use on your machines, on desktop, on Windows. It's part of is an OS component. Then I'm going to cover UWP, which is Universal Windows Platform. Those are the Win10 store applications, and .NET Core. So let's get started with the .NET Framework first. So obviously, there's some kind of Windows layer, and on top of that, we have foundational layer or foundations, some core types like sockets, SSL stream, and DNS listed over here. On top of those, we have HTTP web request with service point and service point manager. That's something that we introduced in .NET Framework 1.0, and it's used by many of our customers, many libraries. It has some kind of limitations, especially around exceptions and or especially around how we handle errors. And we handle them via exceptions, including errors which are kind of normal, like 404. You get exception, which back then, when this was designed 15 years ago, might have been a good idea. These days, it's kind of we would rather like something different. So that's why we worked during the 4.5 time of .NET Framework 4.5 time frame on something called HTTP client with HTTP client handler as an extension model, and it's slightly better architecture. Mainly, it kind of enables pipelining and provides more extensibility than the HTTP web request old stuff. All this design actually of the HTTP client in that time frame was driven by WCF needs. So you see that in the middle layer, HTTP web request is basically written in managed code, and one of the limitations of this stack is actually, for example, we don't have HTTP2 support. That's something that customers asked for. It's a cool protocol, and unfortunately, right now it's not implemented over there. Neither in the HTTP client, which sits on top of HTTP web request and the HTTP web request. Originally, we actually had plans, or the team that actually worked in that back then had plans to eventually switch the HTTP client with the HTTP web request and kind of have the modern API surface of the HTTP client, the full managed implementation, and be directly on top of sockets. Turns out, actually, it's not possible. The key reason is that .NET Framework is famous and loved, especially for its compatibility. If we would do that, I can guarantee that we would break many corner cases and things, and of course we don't want to do that, because if we do that, we break applications. Customers are angry at developers are angry at us, and that's just not something that we cannot afford. So we're kind of stuck in there with the HTTP web request in the middle. So what did we do in UWP? Again, there's some kind of Windows component, or the OS. On top of that, we sits same classes like sockets, SSL stream, and DNS. The foundation are basically very similar. And the HTTP client with the HTTP client handler is actually slightly different than in .NET Framework. It sits directly on top of the WinRT APIs. And the WinRT APIs are actually built on top of Win9.net, which is a client, HTTP stack inside the operating system. The good news is actually that the WinRT APIs were designed around the time when the 4.5 HTTP client was designed, the API surface. And it happened to be exactly the same team. So when you look actually at the WinRT APIs and the HTTP client, they are probably, I think they are entirely the same. Or very, very similar, which is great. It actually causes as well some confusion because people or developers, when they look at stuff, they find out that, hey, why do I have HTTP client in Windows namespace? That's the WinRT API, and in system namespace, that's the managed layer. So that created a little confusion, but I think that we eventually dealt with that. The nice thing about UWP is actually the Win9.net supports HTTP2. So this is the first time we actually were able to provide the HTTP2 protocol for our customers. How does it look on .NET Core? Now, .NET Core has the complication that it's multi-platform. So it works on Windows, it works on Linux and Mac. Linux and Mac are somewhat similar, that's why I kind of merged them in the same bucket. Actually, it should be OS X, but hopefully you're not offended by that. In .NET Core, we have same thing, sockets, SSL stream, and the similar classes built on top of directly on top of the Windows, on top of the operating system. So where's the HTTP client here? So let's look at that. HTTP client does not sit on top of sockets, so it's similar to the UWP, and it has two different implementations of the handlers. So the handlers is the nice extensibility model of the HTTP client. We have one which is WinHTTP handler, which sits on top of WinHTTP DLL, which by the way is server component, and it does support HTTP2, which is great. And on the other side is the curl handler, which sits on top of libcurl and OpenSSL, and does similar things on Linux and Mac. On top of that, we built, or we kind of reintroduced the HTTP web request with service point in .NET Core 2.0. That was part of the big push of the missing APIs we didn't include in 1.0 and 1.1. So we added it back because it's quite used by libraries, and it helps customers to kind of migrate their code from .NET Framework to .NET Core if they want. But because it's higher up, it's it's something that we don't consider as the most performant and most super beautiful thing to do, but it will work, which is important. So what's wrong with this picture, or what are the challenges here? So the challenges we have that the WinHTTP handler and the curl handler are different implementations, so there are differences between them. Of course, the mainline scenarios are the same, but there are many corner cases when actually those things kind of behave slightly differently. What's even worse that on Linux and on Mac, there are differences actually between distros. So some distros have old libcurl working with this. Some of them are not built against OpenSSL, but NSS, and it all causes kind of inconsistency, and our customers suffer. So that's .NET Core how it's today. In the .NET Core 2.0, what do we do with that? So let's look at the future. So I'm gonna get rid of the UWP to make it easier, so you can guys look at that, and let's introduce the future of .NET Core. So not surprisingly, we're gonna have exactly the same layout on the operating system, so Windows and Linux, Mac. Sockets, SSL stream, DNS, again, sit directly on top of the operating system. Of course, we have two implementations for those, one for Windows, actually maybe even three, one for Linux, and probably one for, some differences for OS X. And what we are actually working on right now, I'm going to talk about it even later more, is HTTP client, which sits on top of a managed handler. So it's yet another handler that kind of is written in managed code, that's why it's called managed, and it's built directly on top of sockets, which are kind of specific to the operating system. And again, our friend HTTP web request is built on top of HTTP client as before. So there's no change in there. With this move, we actually, what we hope for, that we're going to get consistency across platforms. performance across Windows and Linux and across various distros of Linux. And we're going to be able to deliver something that customers don't have to test across all those things. And we actually hope that we're going to get even some perf improvements. While we could implement probably some stuff in curl and or in WinHTTP, but it would be rolled out in only the latest version, not available on the distros. So we're kind of fully responsible for the stack over there. The trick will be get as well the HTTP2 and other things. So what do we do with that now? In May, we published this technical roadmap for networking. It's on Designs repo, issue number 9. Look it up if you want to. And we basically outlined something that I just talked about, like kind of 4 key parts of our investments. So the number one is the foundation. That's the blue layer, if you remember from the pictures. Sockets, SSL, DNS. The idea is that should be rock solid. By that we mean reliable, performant, and of course consistent. The other layer that I talked about as the managed client is the web stack. So web stack client over there, we want to focus, as I said, on consistency, because that's something we're missing right now, and on high performance. So making sure that that thing is able to be used really in high performance. Now, if you wonder why client is important as high performance in the kind of role or in the world of microservices, you often have your endpoint of server is not the last thing. It makes a bunch of other calls, and for that you need as well the client side of the networking stack. So that's why it's important. Other thing is actually client WebSocket. I didn't show it in the first picture. It sits kind of on top of all of the components, but that's something we're going to invest into as well. The next kind of thing that we're going to eventually do, or as a kind of like probably in these steps, or not probably, but definitely in these steps, is looking at the emerging technologies, or some of them not so emerging, but kind of newer. So first of all, HTTP2, that's something that we're going to bring, because if we flip out of the current implementation where the HTTP2 is implemented on both curl and actually Windows, we would get rid of that. So we're going to have to implement that in the managed code, so it's going to be lots of fun, lots of work. There are other technologies like RIO, which is registered I/O. It's some new kind of technology in Windows 8+, so that's something that we're going to look at as well. Maybe we will use it, maybe not. Part of that is basically assessing if the technology is worth it. And the other technology you might have heard about lately, it's pretty popular, QUIC, which stands for Quick UDP Internet Connection. It's championed by Google, and I've read somewhere that actually like 20% of internet traffic already is on Quick, because they have implementation in on YouTube and on a couple of their services, and as well in Chrome, and all that stuff actually goes through that. The goal of Quick is basically replacing the UDP and TSL layer in the network, TCP and TSL with something based on top of UDP. The biggest value is actually getting better latency, and anyway, it works. So that's something that we're going to look into eventually as well, see if we can support that and make it available to .NET customers, .NET developers. The fourth bucket is bucket of kind of obsoleted APIs. By obsolete, I don't mean something that we would throw away, but it's something that is on maintenance mode only. Those are things that we don't expect to evolve further. We don't expect to add more in them, more kind of new, latest technology support. We don't expect to make them super performant or something like that. In all cases, we have we have alternatives where we say like, okay, if you used, for example, Mail, go use MailKit. Like that's the, top-notch, latest standards, fast performance thing. If you just need to send 1 email or 100 emails, whatever, you're probably fine with just Mail. But of course, if you're trying to use 10,000 emails, send 10,000 emails, MailKit is your friend. But you're probably a spammer at that moment. Other thing is, for example, the HTTP listener, which is a server. It was very handy to have kind of server inside .NET. We found out, that there's actually not so much need for that. Beside having something like Kestrel and ASP, which is kind of hosting ASP.NET Core. So we're basically telling people, don't use HTTP listener, go migrate to Kestrel. That's your future. And HTTP web request, which has like 2 more things, FTP and file web requests, together with service point. That's basically being replaced for future by HTTP client, as you've seen in the pictures before. So that's our technical roadmap. Now, as I said, we're going to focus on high performance. So what does that mean for us? Let's walk through that. First thing is that we have to figure out and look at and choose scenarios and workloads. There are many options, quite a few options. And one of them, and first and most easy for us and for everyone, is kind of using micro benchmarks. Micro benchmarks are great. And what it is a micro benchmark? It's basically you have small code, piece of code, you can run it repeatedly, it's consistent and thing. They are awesome for iteration and saying like, hey, this is what we're gonna, make sure that it's as fast as possible. The trouble with micro benchmarks is that they don't capture the real world. They are basically very fine-tuned view into what you're doing, what you're doing in the bigger picture. So it's great kind of for iteration and make sure that we iterate on that. But of course, it has to be taken out in the bigger picture, and we have to make sure that we are focusing on the right micro benchmarks. The next thing actually that we're using and is kind of helping our benchmarks, as in larger benchmarks, industry benchmarks. In this case, actually pretty popular is Tech Empower benchmark. So that's one source of actually these micro benchmarks. The Tech Empower benchmark is end-to-end-ish, thing that kind of uses database and everything and makes sure that the entire stack kind of performance is covered and emulates real-world scenarios. Measuring that stuff is great, but when you want to say like, hey, I want to make sure that my networking is great, out of that, it's pretty hard to kind of get the networking in the noise of like database and memory and like the processing of all the protocols above. So that's why kind of out of those things, for our own perspective, we create micro benchmarks, iterate on those, and then come back and measure the benchmarks. And of course, ideally, we would work on, actually, I forgot, two huge advantages of micro benchmarks, both and benchmarks, like Tech Empower, is that you can usually implement them or run them on multiple platforms. So you can compare Dotnet Framework, Dotnet Core, UWP, whatever you want. On top of that, it's actually pretty simple, usually, to run them in other languages. So you can, it's not so simple for Tech Empower benchmark, but it already exists, which means that you have comparison between various platforms, and that's beautiful. In ideal world, of course, we would use real-world scenarios, like real-world applications. Unfortunately, it's rare, I think, as in like it doesn't exist, that someone would have a complex application written in two languages, exactly mapping the same. It was just wasted time. So while real-world scenarios are awesome because that's the real feedback, that's the real usage of the stack or what you're using, it's not really practical for the purposes of comparison and things. But we're definitely looking at that. We're getting feedback from customers via customer support, via GitHub and other avenues. And like often you get like, hey, if I set up sockets or HTTP client or this thing or that thing in this specific way, it's slow or it doesn't perform as I would wish. And we go and dig, and out of that, then we create some micro benchmarks that we can measure, iterate on, and like fix the right things and make sure see what's happening. Oftentimes, actually, it's not in the networking stat. Usually, it's somewhere entirely else. So, what other things do we need when we focus on performance? We need to measure the right things. Here's a kind of example of some of the metrics, or I think these are the most important. RPS, response per second, you probably heard all of them. But this one is about like, web, typically measured in web servers, how many clients I can serve, how many kind of responses I can send to how many requests. Throughput is very, very similar. It's something like how much data can I send? It's typically used in, great example is video and music streaming. That's what you want over there. Latency is important in many scenarios as well, including web. But for example, in a real-time world, when you have, for example, real-time trading, that's usually when it's your key metric. And latency is about like how long does it take me to answer the request. Connection density is an interesting one, emerging lately as well, or it has been there probably forever, but it's kind of more popular and more popular. It's about like how many kind of clients can you handle on one server. Typical examples would be some messaging services like, I don't know, Skype and Facebook Messenger, whatever, or connections to IoT devices, or actually some real devices like hand devices in some company, like, when you don't need sending too much data, but you need to kind of have a live connection, make sure that you can push some notifications, get them back, and that type of stuff. If you have large connection density, you don't have to have so many servers, so you're kind of saving time. All those metrics are not enough. Of course, we have to take into account like percentiles, because it's not usually like, oh, I want like worst case to be this or that. It's usually that you want or average case actually. Usually what you want is like, hey, I need to guarantee that 99% of requests are under this goal, like 100 milliseconds, 10 milliseconds, whatever. You need, another important property to think about is scaling up, which means if I have, for example, 2-core machine and I run the same application on 12-core machine on the same process, kind of same processor's CPU, I expect that I'm going to get 6 times more performance boost. Again, like that doesn't come free. It happens oftentimes that you add more processors or more kind of cores, and suddenly it kind of doesn't give you the linear progression because there's like concurrence and other things. So that's something to pay attention to too. Other thing is as well that resources like CPU, especially utilization, when you measure micro benchmarks, you often like want to peg the CPU, but in real world, in real kind of services, you don't want your system to be 100% packed because bad things happen at that moment. You want to stay away from that. So usually you have like some kind of monitoring system or self-monitoring that makes sure that whenever it's like more than 95% CPU usage, like it's like, okay, like load balance the rest somewhere else to some other server. That's what load balancers are for, all right? Because you want to have some kind of buffer to make sure that when something happens on that machine, that you don't go into the bad state of 100% when then nothing can happen or everything is delayed. So how do we measure that stuff? I'm going to talk a little bit about our perf test environment right now. We're focusing typically on micro benchmarks. That's what I'm going to focus on right now. And key thing in those is repeatability, which means you want to be able to repeat the same test, perf test, and measure it again and again. Because you will have experiments, you will have like different versions, you will have like different languages, and that's what you want. For that, actually, you need isolated environment as much as possible to reduce all the noise. You don't want antivirus kind of kick in. You don't want some other noise on the network to kick in. So what do we do? Right now, all of the measurements I'm going to show you here are basically on 2 machines, quad-core, 16 gig. But the key thing is actually they have 2 networking cards. One is the 10 gigabit, where that's the isolated network where no other traffic comes. And then you have like the management networking card to the external. That's how you connect to the machines, how you run stuff. But that's not where you really measure. And actually, now in November, we're going to get actually cool 8-server setup with 12-core. So it's going to be lots of fun, and especially 40 gigabit networking card. Again, isolated networking. It doesn't mean that we expect that many customers will run with 40 gig networking things, but if we want to be kind of bulletproof, if we want to kind of design for future, we want to be able to see how do we scale up to even those high numbers. If we find out that, hey, for example, around 20 gigabits, it's starting to get like weird and we're not working well, we might say like, you know what, for now it's fine, but let's make sure that eventually we address that. That's something that we want to be aware of. So that's why we kind of are running even micro benchmarks on very beefy kind of networks. All right, so I'm going to show you some perf results, and I want to first do a disclaimer. It's only micro benchmark, so and it's implemented in C#, NET, and Go. Some of those NET and Go implementations might be inefficient. We try to tweak them. We think they are not, but we're not NET and Go experts, so take it with a grain of salt. Don't take it away as like, oh my gosh, like NET is better or worse, or Go is better or C#. That's not the purpose of this talk, and that's not what I'm trying to claim. So let's look at the results. This is what we kind of measured on Linux. So we don't have the Windows results yet, but on 2 CPUs we were able to kind of measure NET Core, NET, and Go, and in each column you see size of the payload. So the micro benchmark over socket is basically send bunch of data other way, receive the same thing. So that's it, very, very simple, no magic. And you can see that the results are kind of interesting. So as I said, in NET, it looks like that it doesn't scale on 1 megabyte and on larger payloads. Again, maybe we just did something wrong. So if someone wants to jump in and help us make it better, and if you have NET experience, please do so. But what we found out actually with the improvements and stuff we did, we were able to get to 1 gigabyte per second actually on .NET Core and Go. So we get to parity with Go, which is pretty cool. and shows that actually even, not even, but the .NET can go to places of really high performance on networking. Interestingly, you can notice that there's some small, gap basically between .NET Core and the other two frameworks on the slower payloads, which means that we have probably higher overhead on per request. So that's something that we're gonna look into. Yes. Actually, over here, yeah. Let's look at the SSL now. So we measured the same thing as well with enabled SSL. Here, the results don't look that awesome, at least for us. NET seems to suck even more, but again, we don't know it's because of our handwritten NET application. But basically there's a 22% gap between the SSL from Go, and actually if you look at the SSL Go versus non-SSL Go, it is basically the same performance. So that's something that we're kind of trying to achieve as well, to basically not only close the gap with Go, but much more close the gap of SSL traffic over sockets being as performant as non-SSL, or as close as possible. Just FYI, these are results from .NET Core 2.0, and the number on the 1 megabyte payload on .NET Core with SSL, in .NET Core 1.1, it was actually half of it. So already during .NET Core 2.0, we were able to actually double the throughput, but there's still place to go and do more goodness. All right. Next results, sockets performance and server. So I'm going to touch a little bit server over here. Kestrel, which is the server for ASP.NET Core, uses today libuv, and we started experimenting with using our sockets in .NET Core, actually replacing the libuv. Motivation is like, again, you get consistency because libuv is external dependency, and you have one less external dependency. Less external dependencies is usually good, assuming we can get to the performance. Some early prototypes showed actually pretty good results with some hacks. We got like 7% improvements, and actually even there, when looking at the results, we saw some potential that we could go even farther. So it would be great with the sockets. Very recently, as in like last week, we actually got some real, re-implementation of sockets, of Kestrel on top of sockets, and the results didn't look that great, but they didn't apply all the kind of lessons we learned from the early prototype. So it's work really, in progress. Actually, 2 days ago, the number 8% was 20%. In last few days, we were able to get that down by just like playing small tricks and kind of applying the things that, towards using the right the sockets in the right way, so that in the right performant way. But you can expect that we're gonna hopefully, or we hope for it, we're gonna get to parity, maybe even farther, and be able eventually swap libuv for sockets. I talked about the managed handler. That's the new implementation, if you remember from the first slide, multi-slide. And it's a thing that we already have. It's early for a functional stage, but you can play with it. And actually, we have some applications that already use it. It's opt-in at this moment. Of course, a prototype, or not prototype, sorry. It's much more beta, let's call it, or pre-alpha, even, I would call it. The key thing that, before we can roll it out and make it even default, is that we have large missing features: authentication, proxy, HTTP2. I think that we can probably ship it like as a reasonable replacement without the HTTP2, but at least the two, will be needed. And of course, we have bugs, and that's what we're going through. Originally, we are kind of hoping that we can pull it off in .NET Core 2.1. I'm a little bit skeptical that we're going to be able to do the big switch and say, like, old, when HTTP and car handle guys go away, we have this managed handler as default. I don't think we will be at the parity, or we might not be at the parity. If we will, we can do that. Or in the worst case, later in 2.2, 2.3. Our early measurements on that thing, again, simple HTTP micro benchmark shows pretty good results. So we have hope that on Windows we got parity with Go. On Linux, there's some 15% gap that we're going to investigate. So overall, we feel pretty good. SSL performance. So there we have quite a lot of indicators that SSL stream, which kind of powers the SSL in our networking stack, is not the best. One of the indicators you've seen earlier in the slides, when we had basically the 22% overhead of the SSL versus non-SSL sockets. So just from the micro benchmark, it pops. We have actually from TechEmpower benchmarks, which ASP.NET runs on a regular basis. They have actually even public data. They compared actually the HTTP versus HTTPS difference investments on .NET Core and as well on .NET Framework and as well on NET and on Go and other places. And it looks like that our kind of penalty for switching to HTTPS percentage-wise is worse than on other networks. So that again shows that, hey, maybe we could do better, and we will try. And of course, we have like ongoing customer reports for years now. They're so far rare enough that we didn't have to pay too much attention, but it's kind of a known thing that, here and there, someone says like, someone's thinking like, hey, we just switched from HTTP to HTTPS and our, throughput dropped 2 times. I'm just making up numbers. But those kind of reports we get. So yes, we're gonna invest into that, and actually this is gonna be investment into .NET Core 2.1. We already attempted, to work on that. There was actually an attempt from community during the summer. Tim Seaward and Ben Adams helped him a little bit, at least with measurements of the SSL stream. What's interesting, I'm calling out here, unfortunately it didn't pay out, we didn't take it. It showed some end-to-end wins on Kestrel scenarios, but when we ran the micro benchmark for the SSL stream, there was basically no change. Which seems like, okay, so we changed something, maybe some timing or something in Kestrel kind of by accident, and it helped. That's not good enough reason for taking, brand new rewrite of a class that it might somehow magically help up the stack. So what we're gonna do is we're gonna, in the next step, make sure that we kind of measure and analyze the micro benchmark, and of course as well the end-to-end scenario, and improve it in .NET Core 2.1. All right. So we're done with micro benchmarks, and let's look at some industry benchmarks or larger benchmarks. As I mentioned, Tech Empower is the one that we are currently or lately working on. It's very end-to-end, as I said. It has databases inside and other things, and it's useful for people to kind of assess the overall platform performance and do comparison. I've just seen recently that there's around 15 preliminary data, where actually ASP.NET Core on Kestrel shows at number 5 entry, which is pretty good, which is jump from number 14 in previous round. Again, still preliminary, but it looks pretty good. So that's yet another reason, or to believe, or to kind of evidence that like .NET can really compete with the top stacks performance-wise. And some of the investments and some of the things that I actually showed you in the micro benchmarks are yet not there yet. So we hope that we're gonna be able to get higher and higher to the top one day. All right. So industry benchmarks, as I said, they are great for people to assess performance of various stacks and basically use it as a guiding. But I want to kind of caution about some things. I strongly don't believe, and I'm not the only one, that performance, is or to that level is something that people should be hyper-focused on. So it shows the potential of your application that eventually, if you care enough, you might get to that. But let's be honest, who writes such hyperscale applications? Like, there's few of them in the world. Maybe 100, I don't know. So it's pretty rare. Yet people say like, oh, performance is the most important thing. Like, it is important, but there's more to kind of assessing platform. It's not the only thing. It's not the only metric. There are many other metrics like, hey, how productivity. For example, if I say like, hey, if I want to be more performant, I should use C++, or maybe write it in assembly. Who would write anything in assembly? Probably no one, right? So productivity, right? I believe that everyone agrees there's a gap. There's other things that kind of play a role, like tooling. Do you have debuggers? Do you have profilers? Do you have like tooling around that? There's actually a key thing is like, do you have developers knowing that particular platform? And either in-house, as in your company, or do you have to retrain them? Is it going to cost you? Or external developers that you can hire, right? And there's as well like availability of documentation. Is there community around your platform or about the platform that you choose? Are there libraries and other things? So overall, I would kind of caution like, don't shoot performance-wise to be, or don't hyper-focus on performance. Like, keep performance in mind, but don't shoot for being perfect on day one. As in like, oh, I gotta pick the top right thing, C++, because it's it's always faster. There are other things that people kind of should consider, and they do usually consider to kind of make the right business balances. The other thing that actually helps when you look at history of all the famous and or some of the famous services that live in the world, like I know Facebook, Google, and other stuff. One of the lessons learned that they often, these kind of services, especially in startup phase, rewrite their stack every 2-3 years. So from the beginning saying like, oh, I'm gonna go shoot after the hyperscale, it's maybe better to, instead of investing like 2 years to get to market, investing just 3 months or something like that, get something out and then work on the performance, and when it pays off, eventually rewrite. All right, I'll stop preaching about that. And here I'm gonna do a short detour about performance and the lessons that we learned over time. So first, you probably know that, but doesn't hurt, kind of to re-educate people again. So first is that performance, you should plan for that in the design time. Ideally, understand the scenario, set goals, like, what's the performance requirements for which metric to use, what matters to you, to your customers, right? Is it latency, is it throughput, connection density, whatever it is. All of those, I don't know. And ideally, like, if you have doubts, like, don't have experience, like, prototype your thing, like, measure early. For example, extreme example would be like if someone goes, oh, I love microservices, I'm gonna turn all my components into microservices. Great idea. If you have 100 of them, guess what? There's gonna be lots of pings between the servers. Maybe your application is not the right, if you need, for example, 10 millisecond responses, that might be a challenge if you have to ping 100 others. Now, if you can ping them, in parallel, maybe it's not a problem. But the point is that if you have some architecture or some design in mind, it doesn't hurt, and it's actually recommended to kind of do a sketch, like think about what kind of volume of data you will run, what kind of requests there will be, what kind of database will be. It doesn't have to be real. There can be fake data. You can just burn CPU, whatever. Nobody cares. But having kind of approximation of what you're doing, making sure that it satisfies your goals, is actually very valuable. Because as we all know, changing the design later in the development phase, like, oh my goodness, you have to basically rewrite. It's a costly thing. Other lesson learned. So optimize for what's important. That's actually a common mistake I have seen all over Microsoft, external customers, whoever. They say like, oh, look, see, I can improve this. Let's go improve that. Kind of, we call it micro-optimization. The first thing always should be, step back. What's the big picture? Does it matter? Right? There's usually the 90-10 rule, which means that only 10% of your application, or sometimes even 5%, are responsible for most of your performance. They are on the hot path. That's where it matters. That's where performance, like optimizing, is great. If you optimize the 90%, which may be responsible for maybe 1% of your performance, does it matter? Do you make it 10 times faster? You just saved less than 1%. That's not going to move the needle for you. But focusing on the right thing is important. For that, you have to measure. You have to have data. Another thing, the last thing, actually, whenever you have a problem, performance problem, don't guess. I've seen it so many times. People look at 1 or 2 dumps and like, oh yeah, I've seen this thing on the call stack. I have to go and super optimize that. Like, no, step back. What's the right thing for performance? Use performance tooling. Like, monitor it, measure it, make sure that you're focusing on the right thing. I have seen so many times people wasting time, and it's like, hey, I saw this in the dumps. I optimized that. It doesn't help. Well, okay, because you optimized the wrong thing. Now you have to do the thing that you should have done in the first place, go measure and look where the time is spent. Part of that is actually minimize repros. That's actually, by the way, applicable to almost anything. You have a bug, you found something, like create a minimal repro. It's so worth it. People always like, oh, I have this gigantic thing, can you help me? It's like, no. Give me more small repro, because guess what's gonna be the first thing if I take your gigantic thing? I'm gonna do the small repro. I'm gonna waste time on that. You're probably better, suited to do the minimized repro because you know what's happening in the thing. And yeah, it's time wasting. But once you have small repro, suddenly your measurements are easier. You can kind of reason about that. You can validate when you have a fix or workaround. It's just so much easier. Anyway, end of detour. So I promise that we're going to get to BCL performance. Looks like that I'm not running out of time, so that's awesome. So let's go to the BCPL performance. Overall, BCL is kind of fine-tuned over the last 15 years. That's how long, how old .NET Native is, or sorry, .NET Native, .NET Framework is. And we don't believe that there are too many opportunities. There are still some. We're gonna get to that. But most of the opportunities on making things better are not about oh, we did something stupid here, let's change that. It's more about oh, you know what? Actually, the workloads we see, it would be nice to make this trade-off. For example, let's rather have one more field, which means sacrifice a little bit of memory for gaining speed, or vice versa. Sometimes it's about optimizing, you know what, in this, the read, for example, well, I'll make it up, read-write lock. Typical workloads are 100 times more readers than writers. So let's make the writer part a little bit slower and the reader a little bit, faster. But basically trade-offs, you're doing trade-offs. It's dangerous because guess what? It just takes couple of, or one workload or one important application that just happens to use the other pattern or the anti-pattern for what you're optimizing, and you're gonna hurt them. They're not gonna be happy. So it's fine line to walk. So how do we identify the scenarios that which matter? As I said before in the performance tip, you should always measure. So what we do, we use customer feedback, and we use that for the 15 years, right? Whenever customers have called customer support, the customer support people come to us and tell us hey, there are these things we were not able to handle that. It doesn't look application. Please help us. So we help them, and that's how we find out oh, people are using this. Oh, it doesn't behave as we thought it should. And this is the scenario. It makes sense. Sometimes we send them back, telling them basically no, you're doing the wrong thing. Just do something else. Tweak it. If you're using the wrong API, it doesn't, we could make it faster, but honestly, you're hurting yourself by just using the wrong API. Now, what's great, that this is much easier in the open source world. So in .NET Core, because there's more people looking at the code, so they can come and say hey, this is actually not as fast as it could be. You could improve it over here. We have actually easier access to reports, so people can report hey, this is not working as fast, or even reliability issues, right, and everything. But hey, this is slow, and then people can upvote, and hey, I hit it as well. So we get very interactive information about things that matter. So that's great. And on top of that, there are motivated contributors. Imagine, and that happens, I think that's the biggest and greatest thing on open source, is that imagine that you're one of the 5 people in the world who hit a bug in a problem, either performance problem or just reliability bug or whatever. Some API doesn't behave as you would like to, but you're 1 in 5. Guess what? There's pretty big chance that we're not gonna get to it anytime soon, but it's open source. So just go and fix that. If it matters to you, you can. You can even pay someone from the contributors or motivate them to help you with that. And there are plenty of people, and we will actually even help. When we see someone is trying to improve things, we will guide them. So that's the great power, that suddenly you have not only access to more data, or we have not only access to more data, what's important, which kind of scenarios, but the people who are motivated to fix them actually have the chance. And to actually prove that, I'm not sure if you've seen this .NET blog post from Stephen Taub about perf improvements in .NET Core. If not, look it up. I think it's 1 month or 2 months old, probably 2 months. We had actually, maybe even more, whatever. There's actually a list of, I don't know, roughly 20, core things that has been improved over time in .NET Core. And if you look at that, actually half of those improvements came from community. Many of them was someone saying yeah, I could make this better. Some of them were oh, it always bugged me that this is slow and I'm gonna make it better. We got great wins in collections. There was sorted set constructor. Actually, by accident, we had n-square algorithm instead of linear algorithm. So guess what? It was 500,000 items, suddenly it's 600 times faster. Yay. Well, hopefully no one will put 500,000 items into sorted set, but people do crazy stuff. Other thing is list.add, it had I believe it had 30% improvement. But anyway, there are basic things that got improved, and that's what we're gonna keep doing. And actually the fact that it's open source is helping us, and you can see that as well. Some of the fixes come from us, some from you, but the key important part to that is that we know what matters, as in we listen to feedback. Another thing actually that's happening in performance, which is in BCL, which is related to performance, is span of t. Not sure if you heard about that. Span of t is very simplified, basically brand new, faster and safe array segment. which works not only on top of arrays, so part of array, but as well unmanaged memory. And it's beautiful. People love it. What it actually brings on its own, it's not performance feature. Actually, if you write unsafe code, you can get a little bit better. But the fact that brings safety via combination of C#, the language support, runtime support, and actually BCL support. That's why we're splitting that. You're gonna get things. You can do things that we couldn't before, or we can do things that we couldn't before, because we couldn't pass suddenly int PTRs around because it would be unsafe code. That would be dangerous. And now with span, we actually can. We don't like adding dangerous APIs. It's dangerous. So those things are that we are doing, and what we should not do, or what we don't take, what kind of investment or what kind of contributions we don't take or what we should not do. So number one thing is specialized collections. Many people say oh, I don't like your direct dictionary. I have better, because for my workload it's better. That happens quite often. The key thing is that, if one person says oh, I have better one, there will be 5 more people saying that I have even better for another workload. So it's kind of unbound problem. You could write collections for ages. So we don't do that, and we never did that. Actually, the BCL is from the beginning designed to kind of be good enough or great enough for majority of customers, let's say 95%. The last 5%, sorry guys, you gotta write your own collection. It's, if you care about specific workload and things, that's what you should do. So we don't want to take those things into .NET Core, into the platform. However, we want to facilitate, there's still value in kind of sharing this code among people, because there are workloads which actually need either multi-value dictionary, or which might actually make it into CoreFX, by the way. But some specialized dictionaries, some specialized lists, and whatnot. So those things we plan, or are working with community to kind of push out into another repo, something like CoreFX extensions, more community-driven, and kind of nurturing the idea that hey, community, you can go play and share these kind of cool specialized collections somewhere. The other thing that we don't take, and is, or where we have to be cautious, is sometimes perf actually cost you, and they cost you in things that not many people anticipate, and that's actually maintainability. If you add code complexity, it's hard to maintain, and it's gonna bite you eventually. For example, link is a great example. We got plenty of things. Oh, in link I can specialize for this, I can specialize for that, and it's gonna be better. And when you look at that, first of all, link is not a performant feature. Link by design is it's basically usability feature for decent performance. We could do infinite number almost of optimizations in there. So we have to sometimes draw the line and say you know what, enough is enough. Or much more how we draw that is okay, what scenarios is this important in? That's what you hear from us quite often. And people say, no, you could do it better. It's going to be 20 times faster. No, I don't care how faster it will be. Tell me why it matters. Is the value adding this complexity, is the cost of adding the complexity worth the value? And for that, we have to be able to articulate what the value is. So those things, we have to be convinced, sometimes we have to convince that it has actually real world impact. So if someone tells us no, hey, I'm using this, and in these things, it's pretty common, or is this pattern in this library and that library, yep, sounds reasonable, let's optimize that. But there we need some data, usually. Other things that are kind of, again, borderline are APIs for some specialized operations. For example, add if doesn't exist, or add or replace, and these type of things. People often want them just because they think oh, I can save this one lookup inside that, and it's going to be beautiful and perfect. The thing is that basically you're leaking the implementation into the API space, and you actually, again, create complexity. It's going to be even harder for people who have no clue and who don't care about performance that much. There's lots of them, by the way. And they will come to the API and say oh, which one should I use? This one, that one, why? How do I choose? Why there are so many functions? Why do I have so much choice? So again, I'm not saying that we never take those, but we have to be extra cautious in the sense are we sure that the saving one internal lookup is gonna be worth it? Is it gonna bring in the real world scenarios really make them faster? All right, I'm done. Last slide. So just to wrap up, what I want you to take away from this talk, first, I want to make sure that you know that we're making proactive investment in .NET networking stack, especially around consistency across platforms, and we won't have great performance for all workloads. So performance matters over there. We're driven by scenarios, and again, reminder, .NET networking stack is not the only thing that in .NET Core we're investing into. I just happen to be very interested in that. So the other thing is that there are ongoing scenarios and kind of feedback-based improvement in BCL, some of that coming from community. So if you want to implement some, or if you want to improve something, something that has been bugging you for ages, you have your chance, go and use that. And the last thing, performance in general, it's important, but it's not the only important thing. You should be aware of that. And it's tricky to get it right in the right place. As in, you should, whenever you do performance, make sure you're focusing on the right thing. That's gonna save you a ton. All right, that's it. So we will have time for questions even. I thought that I'm going to run actually 10 minutes over, and I have 10 minutes before we end up, so.
Вопросы?
Hi. So I want to ask about this famous problem with the full framework HTTP client, which implements iDisposable. Yeah, but when you Google for it, it actually says that it should be single instance in the app. So my question is how this happened, and with .NET Core, do you think this open sourcing will help to avoid such kind of problems, because it's kind of like architectural problem? Thanks.
So I'm not sure if I understood the second question. It's a little bit harder to hear over there, so let me rephrase it. So you asked, about HTTP client being a single instance, if it's still needed in .NET Core. Is that correct?
No.
Okay.
Maybe a step forward, because this previous guy did it. Okay. Can you hear me now?
Yeah, we'll see.
HTTP client in full framework implements iDisposable.
People what? Sorry?
Implements iDisposable.
I see, okay.
Yeah, but it's actually seems to be that it's used as the single instance.
Yep, in many cases.
So
although there are patterns where actually the single instance is a bad thing because, for example, DNS and other things changes. So yeah, it's a problematic thing.
Yeah. So the question, but there is still a big problem with that, because when you Google it, you don't know which variant should you use. So the question is, will open sourcing .NET Core help with such problems? The design will be better, but it's really architectural design.
Yeah. So first of all, we don't, at this moment, we don't plan to change the APIs. So if iDisposable is on HTTP client, it's as well in .NET Core. Our key thing is to make sure that what works on one platform works on the other as well. Now we are open to kind of make drastic changes to the API design, but not in the sense let's break it. But I would be okay experimenting like HTTP client 2 or something like that if we find that it's worth the complexity, it's worth introducing yet another thing. If the benefits are, if the problems we're going to solve are really, the benefits are so great that it's worth it to make something like that. So it's up on the table. I would put it somewhere between if you saw the number of things, what to focus on, between the 2 and 3, and it's really if it happens. I don't know if it's going to happen. Does it answer your question? All right, kind of, yeah. We can talk offline later if you want to as well. Any other question?
Не вижу.
And before I hear the other question, so if you want to talk with me, feel free to find me anywhere. We're gonna be in the discussion zone, of course. But today, in the party, or if you see me walking around, I love talking about anything .NET Core. You have questions, you have success stories, you have something that bugs you, like HTTP client, iDispose or something. Please come to me. That's actually for us and for me. It's yet another customer feedback, yet another +1 on the problems or on the positive things that we can take into account. So please come to me.
Hi, yeah, Dmitry Naugolnych, Arcadium. So thank you for the great presentation. You have mentioned that anyone can commit into the project if something is paying for him for a long time. And my question is, are there any requirements? If, for example, I do not have any pull requests or stars on GitHub, I'm still eligible to commit something, to send pull requests to you?
So we have actually I would love to say great, but it's almost great documentation of how to start for first-timers. So if you look CoreFX GitHub repo, so it's http://github.com/.net/CoreFX. On the first page, you're going to get link actually into our wiki for reasons I'm not going to get into right now. And over there, there's actually steps how to do that for even beginners who never did any Git, who never did any GitHub. So that's something that should get you started. If not, ping me. I don't have it over here, but Karel Z, Karelz on GitHub. I'm helping constantly new contributors. We're open to anyone. We're going to help you.
Okay, thank you.
Sure. Anyone else? Over here.
Hello, thank you for your talk. I'd like to ask, for a problem I had recently, I had to send one web HTTP request, but I had to configure a TLS, but just for this request. And currently, the only way to configure it is via service point, which is a global static thing. And I had a problem that I had some other HTTP clients in other threads that had to have other TLS settings. Is it fixed somehow in .NET Core, or is it an architectural thing, or what?
So I don't know. Let me put it this way, from top of my head. What you said, how a service manager is service point, and service point manager is for the HTTP web request, and then you talked about HTTP client. So that's even for me a little bit mixed up. But even if we get it right, I'm afraid that I will not be able to answer the question because I really just don't know. The best thing, go on GitHub, file a question, try it out. Create a small repro. Hey, I did this. Try it out. If it doesn't work on .NET Core, file a bug. It's pretty simple. You just have to have an account on GitHub, and we are responsive to those things. Like, we look into things. So,
thank you.